Track for Hi guys, good afternoon. Um am I audible? Can you please confirm in the chat window if I'm audible? For those who feel that I'm not audible, you can just log out and log in, please. Right? Perfect, perfect. All right. So this is the agenda of today's session, right? So what I've done is I'm going to split this number system session into two parts. Okay. We're going to have the first part this week, and we're going to have the next part of the number system in a couple of weeks' time. So the first part of number systems is going to deal with the basics of numbers. How do you figure out what is a terminating, recurring? How do you plug in some values? And some questions based on that. Okay, so I'm going to deal with questions of the 600, 650, the mid 600 levels, right? And towards the end, I'm going to deal with some challenger questions based on the topics we discussed today. And the second part of the number system webinar will be focused entirely on questions of a 700 level. Okay, so the feedback given by students for our webinars was they wanted something to be, they wanted us to cater to all different types of students. So they wanted us to take up a session for questions in the mid 600 to 700s and then move on to the more complex ones, right? So all right. So quickly, if you can type in the chat window, we're going to start in exactly 1 minute. So quickly in that 1 minute, if you can type in the chat window what you are expecting or what is the take back that you would want from this session, I can also cater to whatever suggestions you give me. So quickly, guys, can you please type in the chat window what problems you face with number systems? What would you want me to discuss number systems? And also is there specific types of questions that you want to discuss also? Okay, Deepak, fine. Okay, techniques for remainder questions. Okay, I'll speak about remainders a bit. All right, fine. Anything else? Any other suggestions? Okay, complex fraction questions. Okay, finding digits place problems. Okay, so you want me to deal with what are unit digits and so on? All right, fine. I'll try to fit in. I'll try to fit in whatever suggestions you've given me. I think the set of slides that I've made for this entire session should take care of a couple of things. There are tricky DS questions. There are questions on factors. There are questions on factorials. There are questions on remainders. So I'll try to cater to all aspects of things. I'm going to give you like some background explanation before I jump into giving you questions. So that's how we will start the session. Okay. So let's begin the session, guys, and I'm going to share my screen with you, right? I'm going to share two screens. One is a PPT as well as Word file so that I'll be able to write on it. So just let me know if you're able to see my screen, please. So there should be a Word file uh, right in front of you. So quickly confirm if you're able to see my screen and I can start. Perfect. All right. Perfect. So I'm not going into the basics of what numbers are. You already know how numbers are classified, what are natural numbers, whole numbers, integers, and so on, right? What I'm going to deal with first is the concept of fractions. Now, if you remember what you studied in school, fractions can be classified into two types, right? You can have fractions to be proper fractions and fractions to be improper fractions. The easiest example of a proper fraction would be half, 1/4, or the definition of a proper fraction is when the numerator is always lesser than the denominator. And an improper fraction would be of the form 5/3, 7/5, or the definition of it would be when the numerator is always greater than the denominator. Now the thing with fractions is, right, you can convert fractions to decimals and you can also convert decimals back to fractions. But if you consider fractions in their decimal form, fractions can be classified as terminating fractions and non-terminating fractions. Now, can you all please give me an example, maybe type it in the chat window. Can you give me an example or a couple of examples for a terminating fraction and a couple of examples for a non-terminating fraction? Perfect. So most of you are giving me half as terminating and 1/3 as a non-terminating, right? Perfect. All right. So I'll work with the examples that you've given me. So the reason why you're telling me that half is a terminating fraction is when you convert the half into a decimal, you get a finite number of elements after the decimal point. And the reason you're telling me that 1/3 is non-terminating is because when I convert 1/3 in its decimal form, you're going to get an infinite number of elements after a decimal point, right? Now, it's safe to say that the definition of a terminating fraction is a fraction is said to be a terminating decimal if there exists a finite number of elements after the decimal point, and a fraction is said to be a non-terminating decimal if there exists an infinite number of digits after the decimal point. But this basic definition, right, is not going to help us to figure out whether a fraction, looking at a fraction, whether it's terminating or not. So what I'm going to do is I'm going to give you all a list of fractions, some random fractions from the top of my head, right? And I want you guys to tell me whether the fractions that I'm writing down here are terminating or non-terminating. Okay, and whatever answer you give me, I want you to logically, quickly type out what is the logic behind you telling me that this fraction is terminating and this fraction is not, right? So I'm going to give you a list of around 6 fractions, 7/27 being the first, 17/80, 11/225, 11/222, 9/256, finally 72/3000. So my question here is, can you tell me which of the 6 fractions are terminating and which are non-terminating? Remember, I don't want partial answers, okay? I want all the fractions which are terminating and all the fractions which are non-terminating. Okay, so most of y'all, okay, 2, 5, and 6 says Rishi. All right, somebody says 2, 3, and 5. Okay, so a lot of y'all are telling me that 2, 3, and 5 are going to be terminated. Some say 6, 2, and 5. Okay, perfect. 1 and 2 only. All right. Now this is where you need to. Okay, so a lot of non-terminating. All right, so some of you all have given me the right answer, some of you all have given me partial answers. Okay, so just listen to me in terms of how I would define a terminating fraction, and towards the end of the explanation, right, you will be able to identify whether a fraction is terminating or not very easily. Now, for a fraction to be terminating or not, right, everything depends upon the denominator of all the fractions you're dealing with. Okay, it all depends upon the denominator of the fractions you're dealing with. Now, what I'm going to do, and this is what I don't want you to do on test day. I'm just going to first explain to you what is the definition that you need to hold on to for a terminating fraction, and the definition you need to hold on to for non-terminating fraction. And towards the end, right, when after I give you the definition, I tell you how to approach this problem. That's the point that you need to hold on to what I'm going to say. Now, like I said, right, for a fraction to be terminating or not, everything depends upon the denominators of the fraction. What you're going to do with the denominators of the fraction here is you're going to prime factorize the denominators. 27 can be written as 3 into 3 into 3, which is 3 cubed. 80 is 16 into 5, and 16 into 5 is 2 to the power of 4 into 5. 225 is 15 square, and 15 square can be broken down into 3 square into 5 square. 222, for those who don't know how to break down 222, just go on dividing it. This divides by 2, that's 111. 111 is perfectly divisible by 3, so 3 3s are 9, 3 7s are 21, and 37. So this is 2 into 3 into 37. 256 is 2 to the power of 8. It's mandatory. You guys know what the powers of 2 are from 1 to 10. Those are standard values that the GMAT would test us on. Okay. And I'm going to keep the 72 by 3000 towards the end. Okay. I'm going to come back to it in the end. So now what you need to hold on to here, is the actual definition of a terminating and a non-terminating fraction. A fraction is said to be a terminating decimal. Listen very carefully, please. I'm giving you the actual definition you need to hold on to. A fraction is said to be a terminating decimal if the denominator consists of only 2's, or the denominator is of the form 2 to the power of m, or 5 to the power of n, or 2 to the power of m into 5 to the power of n only. Or in simpler words, if the denominator consists of only 2's, only 5's, or only combinations of 2's and 5's, then only we can consider that fraction to be terminating, right? So this is the definition of a terminating fraction that you need to hold on to. That's much more important. That's much more important than the fact that, you know, a terminating fraction is one which has an infinite number of elements after the decimal point. Remember, whenever you need to figure out if a fraction is terminating or not, you need to look at the denominator. If the denominator can be broken down to only 2's, only 5's, or only combinations of 2's and 5's, then that fraction is said to be terminating, right? So if this is the example, or this is the definition of a terminating fraction, then a non-terminating fraction can be defined as a fraction where the denominator consists of anything other than 2 and 5. So a fraction is said to be non-terminating if the denominator consists of anything other than 2 and 5. For example, 3, 6, 7, 9, 11, 17, and so on, right? If the denominator consists of a 3 or a 6 or a 7 or a 9, you can directly eliminate them to be non-terminating. So if I have a look at these 6 fractions, what I don't want you all to do is to prime factorize the denominators. What I want you all to do is to hold on to the definition of terminating and non-terminating, glance at all the fractions, and eliminate the fractions which are non-terminating. Now the definition of a non-terminating is if the denominator consists of anything other than 2 and 5. So doing a vertical scan on the answer choices, I have the first answer choice to be 7 by 27. So clearly the denominator here is divisible by 3. So this fraction is definitely non-terminating. I hold on to 17 by 80 because I know 80 is 16 into 5, that's 2 to the power of 4 into 5. That's only consisting of 2's and only consisting of 5's. 225, the denominator here is 2 plus 2 plus 5. 2 plus 2 is 4, 4 plus 5 is 9. Since the sum is 9, I know 225 is definitely divisible by 3. So I can directly eliminate it as non-terminating. The same holds good with 222. 222 also gives me a denominator which is perfectly divisible by 3. So 222, 11 by 222 is also non-terminating. 256 is 2 to the power of 8, so I hold on to 2, I hold on to 5. So what I've done, only by looking at the denominators of all the fractions and seeing if it's divisible by anything other than 2 and 5, I've eliminated the fractions which are non-terminating. It's very easy for you to eliminate which are non-terminating. For the ones which are terminating, you have to make sure that the denominator consists of only 2's, only 5's, or combinations of 2's and 5's. So if I give you 72 by 3000, based on what we discussed right now, would 72 by 3000 be a terminating fraction or a non-terminating fraction? Would 72 by 3000 be a terminating fraction or a non-terminating fraction? No, this would definitely be a terminating fraction. So what you need to hold on to here is, whenever you're checking whether a fraction is terminating or not, you have to make sure, and it's mandatory you do this, you have to make sure that the fractions are reduced to its lowest form. So 12 6 is 72, 12 2 is 24, 12 5 is 60, 0, 2 3 is 6, 125. So 72 by 3000, the lowest form would be 3 by 125, and 125 is 5 cube, which only consists of 5s. So the last fraction is definitely terminated. So the terminating fractions here are 2, 5, and 6. Okay with this, guys? So remember, what you need to hold on to here is for a fraction to be terminating, the denominator should consist of only 2's, only 5's, or only combinations of 2's and 5's. Non-terminating, the denominator can consist of anything other than 2 and 5. But remember, whenever you're checking whether a fraction is terminating or not, you have to make sure that you reduce the fraction to its lowest form. All right? So can I move on to the next concept? I'm just quickly giving you a revision of all the topics involved. I'm going to go also in terms of roots and give you some questions. So I'm going to first explain some concepts and then go to a set of questions. All right? All right. I'm just moving on to a new screen. Okay, so now. Non-terminating fractions, right? Non-terminating fractions are of two types. The non-terminating fractions can be recurring. They can also be non-recurring. Can you give me an example of a fraction which is a recurring decimal? Can all of you type in an example of a fraction which is a recurring decimal? Perfect, 1 by 3. Can you give me an example of a number which is a non-recurring decimal? No, I'm not going to accept 22 by 7. I'm not going to accept 1 by 7. Okay, I would accept pi. I'll definitely accept pi. I'm not going to accept 22 by 7. Any other example other than pi, which is non-recurring? I'm not going to accept 1 by 7. Hi guys, can you hear me? I think there was a slight fluctuation with the internet. Can you please type in the chat window if you're able to hear me, and I can share my screen again with you. Perfect, perfect. All right. So, is my screen audible? I mean, is my screen? Are you able to see my screen? I'm also audible. Can you please confirm that, and I can start off. Continue from this point. Perfect. All right. So, like I was asking you, right? Can you give me an example? Can you give me another example other than pi? Exactly. Roots. Roots are also numbers which are non-recurring. I'm not going to accept any fraction under a non-recurring decimal. Okay. I'm only going to accept roots and pi. The reason you're doing that is for those of you all who told me 22 by 7 and those of you who told me 1 by 7. If you divide 1 by 7, right, you're going to get 0.142857. Again, it's going to repeat 142857. You're not going to get a set of values which are non-recurring. See, the meaning of the word recurring is there should be a repeated set of digits, or one digit being repeated, or a set of digits being repeated. I cannot accept 1 by 7 or anything divided by 7 to be non-recurring, because the digits are going to recur after every 6th decimal place, right? So the reason why you gave me 1 by 3 as an example of a recurring decimal is because when I convert 1 by 3 into a decimal, I'm going to get 0.33333, which can be represented as 0.3 bar right? The bar on the digit which repeats. Now my question is, if I give you a recurring number that's 0.15151515, that's 0.15 bar, and I ask you to convert this recurring number into a fraction. So I want the fractional equivalent of 0.15 bar. What would be the fractional equivalent of 0.15 bar? What would be the fractional equivalent of 0.15 bar? Anybody? No, 1 by 6 is not right, 15 by 100 is not right, 15 by 9 is also not right, 15 by 100 is an approximation, Sanjana. See, I want the exact value of the fraction, right? I want the exact value of the fraction. So this is how you convert a recurring number quickly into a fraction. Okay, so the rule is, you write down the recurring number 0.15 bar, you take the digit after the decimal, you place it on the numerator, right? You take the digits after the decimal and you place it on the numerator. On the denominator, you need to look at how many digits are under the bar. So here in this question, we have 2 digits under the bar. That's 1 and 5. And the rule is, for every digit under the bar, you're going to place a 9 on the denominator. So 0.15 bar can quickly be written as 15 by 99. And if you simplify to the lowest form, this would be 5 by 33. Similarly, if I give you 0.23 bar, then the fractional equivalent would be 23 by 99. I'm going to repeat. You're going to take the digit after the decimal, you're going to place it on the numerator. You need to see how many digits are under the bar. The rule is, for how many ever digits are under the bar, you place that many 9s on the denominator. So if I give you 0.645, the bar on 645, the answer clearly here would be 645 divided by 999. All right. Now, what if I give you 0.23, the bar on 3? What if I vary the positioning of the bar? What would be the fractional equivalent of 0.23, the bar on 3? No, 23 by 9 is 2 point something, right? I mean, think about it logically. 23 by 9 would be 2 point something, right? So it's not going to be 0.23333. Exactly. So this is how you work. This is how you work when the positioning of bar is varying, okay? You take the digit after the decimal, you place it on the numerator. You subtract what is not under the bar. You take the digit after the decimal, you place it on the numerator. You subtract what is not under the bar, divided by. The rule for any digit under the bar is you place a 9 on the denominator. And the rule for any digit which is not under the bar is you place a 0 by default. So if I give you 0.23, the bar on 3, that would be 23 minus 2 divided by 90. That's going to be 21 by 90. Dheeraj, 233 by 10,000 is still not 0.2333333, right? I need the exact fraction for it. I can't give an approximation for it, right? So if I give you 0.645, the bar on 45. So again, same procedure holds good. You're going to take the digits after the decimal. You're going to place it on the numerator. You're going to subtract what is not under the bar. And what is not under the bar here is 6 divided by. For a digit under the bar, you're going to place a 9 on the denominator. So I'm going to place 2 9s here. And for a digit not under the bar, you're going to place a 0. So 645 minus 6, that will be 639 divided by 990. And you can reduce this to the lowest form, right? So that's how you convert any recurring number into a fraction. Okay with this, guys? So I'm just giving you this basics because the questions that I have here deals with this, okay? So you'll need to know how to convert a recurring number into a fraction. You'll need to know how to identify a terminating or a non-terminating fraction. Okay with this, guys? Any doubts on what we discussed in terms of terminating and recurring quickly? What about numbers such as 6.45 with bar? No problem, Mayank, so even if you have a 6.45, right? The bar can only be on the digits after the decimal, right? The bar can only be the digits after the decimal. So you just split this up as 6 plus 0.45 bar, right? So this would be 6 plus 45 by 99. Simple as that. Okay, why will I not take any fraction as non-recurring? Because any fraction you take, Sanjana, and if you make it into a decimal form, the digits are going to repeat at some point or the other. For example, if you take 1 by 7, right? 1 by 7 will be 0.142857, again 142857. So basically I can say that when you divide a number by 7, it's going to recur after every 6 decimal place. If you divide a number by 6, right? 1 by 6 will be 0.1666666. Whenever you divide a number by 6, the digits will recur after every second decimal place. If you divide a number by 11, it will be 0.090909. The digits will repeat after every second decimal place. So if you go on dividing numbers here, right, you'll realize that as you go on dividing numbers, there's always going to be some point in which the digits are going to repeat. That's why you don't have any fraction as non-recurring. The other way of defining a non-recurring fraction, right, or the other way of defining a non-recurring number, non-recurring numbers are always irrational numbers. Now, what are irrational numbers? Irrational numbers are roots, right? Irrational numbers are roots. Roots are referred to as irrational. Okay, so root 2, root 3, root 4, right? Not root 4, root 5, root 6, and so on. So we call them irrational. All right. Okay with this, guys. So do you know how to convert a terminating, how to figure out a terminating fraction, how to convert a recurring number into a decimal, or recurring decimal into a fraction? Okay with this, so that I'm just giving you like a background of this concepts, because my first 4 questions deals with this. Okay, can I move on? I want to also make one more point before I give you some questions. All right, perfect. Okay, so just before I give you some questions, there's another point that I want to make here. See, I just told you that non-recurring numbers are irrational, right? And I gave you an example of irrational numbers to be roots, root 2, root 3, root 5, and so on. Now, my question to you is, see, it's mandatory. You need to know the formula of how to work with roots. So root of a into root of b is root of ab. Root of a divided by root of b is whole root of a by b. Root of a plus root of b is just root of a plus root of b, right? You can't simplify this algebraically. Now, my question is slightly different here, right? My question is, if I give you exponents, that is powers, right? Say 2 to the power of 12 and 3 to the power of 8. Or I give you fractional exponents, say 2 to the power of 1 by 4 and 3 to the power of 1 by 5, right? Now, my question to you is, let's compare these two values first. If I give you 2 to the power of 12 and 3 to the power of 8, out of these two values, which one is the greater of the two? Is 2 to the power of 12 greater than 3 to the power of 8? Or is 3 to the power of 8 greater than 2 to the power of 12? How would I figure out which ones of the two is greater? Guys, did you understand my question? My question is, if I ask you to compare 2 to the power of 12 and 3 to the power of 8, which one would I say would have the greater value? Okay, how does it depend on the base, Mayank? Exactly. So whenever you're comparing two exponents, right? The best thing to do is, if you want to find out which one of the two is greater, is you always make sure that you make the powers the same. So what happens if you make the powers the same, you can always compare the bases, and whichever number has the greater base would be the greater fraction, right? Now here, whenever you're comparing two exponents, right? Whenever you're comparing two exponents which are integers, the best thing to do is to always take the HCF of the powers. Okay. Now, what is the HCF? What is the highest common factor of 12 and 8? What is the highest common factor of 12 and 8? 4. So I can rewrite this as 2 cube to the power of 4, and I can rewrite this as 3 square to the power of 4. So what's happening here is I'm keeping the exponent to be equal. So now I just need to make a comparison of the base for me to comment upon which term is greater and which term is lesser. So this can be written as 8 to the power of 4, and this can be written as 9 to the power of 4. So the rule is, whenever you need to compare integer exponents, or whenever you need to compare numbers with integer exponents, you always take the HCF of the powers and you make the powers equal. So once you make the powers equal, all you have to do is make a comparison between the bases. Now, which would be the greater, going on to the next condition, which would be the greater out of 2 to the power of 1 by 4 and 3 to the power of 1 by 5? Out of these two, which would be greater? Is it the 4th root of 2, or would it be the 5th root of 3? Guys, can you hear me? Would it be the 4th root of 2 or the 5th root of 3? I've got only one answer yet till now. Okay, some say 5th root of 3. All right. Okay, I've got a couple of 2s also. All right. Let's look at how we exactly, find out which of these two is going to be greater. Whenever you're comparing fractional exponents, the best way to compare the fractional exponents is again to make the powers equal, right? But the best way to make the powers equal here when you're dealing with fractional exponents is to take the LCM of the denominators of the powers. Now the LCM of 4 and 5 here is clearly 20, right? The LCM of 4 and 5 clearly here is 20. So I can rewrite this as 2 to the power of 5 by 20, since 1 by 4 is 5 by 20. And I can write this as 3 to the power of 4 by 20, since 4 by 20 is 1 by 5. Now what I'm basically trying to do here is trying to make the powers the same so that I can make a comparison between the bases. So this can be rewritten as the 20th root of 2 to the power of 5, and this can be written as the 20th root of 3 to the power of 4, right? So the prerequisite here is, you guys know that fractional exponents are roots itself, right? So if I say 2 to the power of 5 by 20, I can write it as the 20th root of 2 to the power of 5, and here I have the 20th root of 3 to the power of 4. Now what is 2 to the power of 5? 2 to the power of 5 is 32. So this is the 20th root of 32. But 3 to the power of 4 is 81. So this is the 20th root of 81. So when I make a comparison of these two quantities, it's very, very clearly evident that the 20th root of 81 is much greater than the 20th root of 32. So 3 to the power of 1 by 5 is the greater of the two. So in a nutshell, this is what you need to do. Whenever you're comparing exponents, the rule is you always make the powers to be equal. How you make the powers to be equal will depend upon whether you're dealing with integer exponents or fractional exponents. When you're dealing with integer exponents, you always make the powers equal by taking the HCF of the powers. And when you're dealing with fractional exponents, you always make the power equal by taking the LCM of the denominators of the powers you're dealing with. All right? So you always try to make the powers equal, and you always make a comparison between the bases. Okay with this, guys? All of y'all, any doubts on this? Yes, Kiran, you can tell me your doubt. Yes, Kiran, what about 20 root 81? If I give you the 20th root of 32 and I ask you to compare it to the 20th root of 81, Kiran, this is basically 32 to the power of 1 by 20 and this is 81 to the power of 1 by 20, right? So this clearly is greater because the power is the same, right? The one with the greater base has to be the greater value. So if I give you the fourth root of 3 and the fourth root of 5, it's clear that the fourth root of 5 has to be greater, right? Because it has the bigger base, isn't it? Right? Just have to compare the bases. Okay, guys. So clear with this. Clear with this. I just wanted to put this basic aspect of things in place and get this out of the way because I've I've kept a couple of questions, around 3 to 4 questions, which deals with terminating, recurring, as well as a comparison of integer exponents and fractional exponents. So can we move on to the questions? If you tell me yes, I can directly share the PPT with you. Perfect. So this is the PPT, and this is your first question. Okay. So again, I don't want any of you all to type in the answer in the chat window. Please type in the answer only once I say that your time is up, right? And I give you around 10 seconds to type your answers in. Uh, Again, 2 minutes per question. I'm going to stop the timer at the end of 2. So your 2 minutes for this question begins now. Another 30 seconds to go. You can start typing your answers in the chat window, please. Guys, you can give me the answer in terms of A, B, C, D, and E, okay? Okay, so I see a lot of contradictions, lots of C's, lots of B's, some with E's, some with A's. Okay, lots of contradictions. All right, last 10 seconds before we have a discussion on this question. Guys, I see 40 and odd people that logging into the session, so I would want an answer from everybody, please. So even if you're not getting it, I would want you to give me the best possible answer, all right? All right. So let's have a discussion. Okay, let's have a discussion on this question. Now, see, the basic crux of what we discussed in the concept before is going to be used here, right? But the problem here is we've been given three different exponents. So the better thing to do is it's the same as this, right? If I give you three people and I ask you to find out, or I ask you to arrange them in height order, you would basically take two people, compare the heights of each other, take the taller person, compare that with the third, that would be my tallest, and then compare the remaining two to give me who would be the shortest, right? So I'm going to do exactly the same thing here. I'm first going to take 2 to the power of 120 and 3 to the power of 72, and I'm going to compare these two, right? Since I'm dealing with integer exponents, I know that I need to make the powers the same. So I need to make the powers the same by taking the HCF of the integer exponents, right? So what is the HCF? What is the highest common factor of 120 and 72? If anybody can type it out, highest common factor of 120 and 72? 24? No, Preeti, 12 is not the highest common factor. 24 would be, right? Because 24 into 5 is 120, 24 into 3 is 72. Perfect. So the highest common factor here is 24. So I'm going to keep the powers the same, right? So this is going to be 2 to the power of 5 into 24. And this is 3 cube into 24. So now if I make a comparison of this is going to be 2 to the power of 5 is 32. So 32 to the power of 24, which I am comparing with 27 to the power of 24. So clearly here, 2 to the power of 120 is greater than 3 to the power of 72, right? So now I'm going to compare 2 to the power of 120 with 17 to the power of 30. Looking at the powers itself, we know that the HCF here is going to be 30. So this is going to be 2 to the power of 4 into 30. And this is going to be 17 to the power of 30. 2 to the power of 4 is 16. So that's 16 to the power of 30. And that's 17 to the power of 30. So clearly, 17 to the power of 30 is the greatest of my three terms, right? And the question asked me to give me the answer in terms from smallest to the largest. So the largest has to be 17 to the power of 30. The next smallest has to be 2 to the power of 120. And the smallest here has to be 3 to the power of 72, right? So 3 to the power of 72 is choice 2. 2 to the power of 120 is choice 1. And 7 to the power of 30 is choice 3. So the correct answer would be 2, 1, 3. That would be Charlie. Okay with this, guys? Okay with this, I just gave you a GMAT type of question based on the concept of HCF and LCM of the powers. Okay with this? Everybody, any doubts in this question? Perfect. So there were a lot of contradictions. I think some of you all made a very bad mistake of giving me the largest to smallest, right? You can't make such mistakes on the test. Those are very silly mistakes. Those are the mistakes you need to avoid. All right. Perfect. So I'm going to move on to the next question, right? Again, same rule applies. Please do not type in the answer in the chat window until I mention, that 30 seconds more are left. So here's the second question. Your 2 minutes start now. I don't think you require 2 minutes for this question, but I'll give you 2 minutes. All right. So here's your second question. All right. So last 30 seconds, you can type in your answers now. Perfect. So most of you all have given me the right answer. Very, very simple to work this out. The answer is definitely B. So the question is, if m and n are integers, what is the smallest possible value of integer m such that m by n is 0.363636, right? So here I have this as 0.36 bar. So 0.36 bar can be written as 36 by 99. And remember, I need to reduce this to the lowest form. So 9 fours are 36, 9 11s are 99, right? So the answer here has to be 4 by 11, right? So why did most of you all give me B to be the answer 4? My question was, what is the smallest value, what is the smallest possible value for M, right? I didn't ask you, some of you all gave me the answer to be 11. I didn't ask you for the smallest possible value for N. I asked you for the smallest possible value for M. So the smallest possible value for M here is going to be 4. Okay, but this guys, very, very simple one. This was a very simple one. Just I'm going to build from here, right? So I'm going to make it a little more complex in the next question. So for those who didn't get this, this was a very easy one. So you should make sure that these questions are answered very quickly. All right. So I'm moving on to the next question. Here's the next question. Again, take 2 minutes. Please do not type in the answer in the chat window until I tell you to, please. Okay, guys, you can start typing your answers in the chat window, please. All right. So I see a lot of E's, some C's, some with A's, some with B's. So most of you all are giving me E to be the answer. Some of you all are giving me C. Okay, so let's work it out. All right, let's work it out. Now, like I said, right, like I said, for a fraction or for a number to be a terminating decimal, the denominator should be consisting of only twos, only fives, or only combinations of twos and fives. But if the denominator consists of anything other than 2 and 5, right, I can directly classify it as a non-terminating fraction, right? Siddharth, I don't think, I mean, I think you're preparing for the GMAT for the first time. So this is a data sufficiency question, right? So a data sufficiency question has 5 answer choices, which all students are expected to know, right? So the first answer choice is alpha, 1 alone, 2, and so on, right? So I'm not going to deal with that right now because just a waste of time, right? Now, I'm going to deal with the first statement. The first statement says 24x is an integer, right? Now think about this, and they've also told me that x has to lie between 0 and 1. So I know x here is definitely a proper fraction, right? And the question is asking me, is it possible to write x as a terminating decimal? So what you need to do in a data sufficiency is you need to check whether the information given in the first statement is sufficient to answer the question or not. So the first statement tells me 24x is an integer. So I'm going to think about what values of x or what fractions of x would make 24x an integer. So if I keep x to be half, right? If I keep x to be half, I know that 24 into half is definitely an integer because it gives me 12. So x can definitely take a value of half. And is half a terminating decimal? I get a definite yes to the main question. But I can also take x to be 1 by 6 or 1 by 3 to make it more simpler. Because 24x here is going to be 24 into 1 by 3, which is 8, which is still an integer. So x can also take a value of 1 by 3. Now in this case, I'm going to get a no, since 1 by 3 is definitely not a terminating decimal. So the first statement is clearly insufficient. The 3 possible answer choices are B, C, and E. Now coming to the second statement. The second statement tells us that 28x is an integer. So clearly looking at it, I can have x to be 2 or x to be half, because 28 into half is 14. In this case, half is definitely a terminating decimal. Or I can have x to be 1 by 7. If I have x to be equal to 1 by 7, then 28 into 1 by 7 is going to be 4. So this gives me a no, since 1 by 7 is definitely not a terminating decimal. So the second statement also clearly is insufficient individually. Now, when I combine the two statements, I have two pieces of information. I have 24x to be an integer, and I also have 28x to be an integer. So think about this, guys, okay? And this is mostly for the people who have given me echo as the answer. Can you think about a fraction x which divides both 24 as well as 28? Can you think about a fraction x which divides both 24 as well as 28? Can you give me an example of a fraction x which divides both 24 as well as 28? Clearly 1 by 2, 1 by 4. Any other fraction would divide both? See, in this case, 1 by 2 would give me a yes. In this case, 1 by 4 would give me a yes. Is it possible for me to select a denominator for x which is something other than 2 and 5 and which divides both? Tarun, 24 into 1 by 7 is not an integer, so I won't be able to use that. Is it possible for me to choose a fraction where the denominator is anything other than 2 and 5, which makes 24x and also 28x to be an integer? I definitely cannot get a value for x where the denominator is something other than 2 and 5. Then 1 by 7 will only satisfy the second statement. It's not going to satisfy the first. So the only possibilities I have that is going to satisfy this entire statements together are going to be values where I'm going to get the denominator to be only 2's and only 5's or only combinations of 2's and 5's. For example, 1 by 2, 1 by 4, and so on. I will never be able to get a scenario where I'm going to get a no to disprove this entire set of statements. Okay, with the guys, I just wanted to know Guru Prasad, this is not a value data sufficiency, right? It's not a value data sufficiency. This is a yes no data sufficiency, right? So a yes no data sufficiency, you need to answer the main question with a yes or a no. Yes, it can be two or it's multiple. So 1 by 2 would be an answer, 1 by 4 would be a possibility, right? Even anything in terms of say 2 by, so 6 by 7 is also a possibility, right? Because I know 24 can be perfectly divisible by 6, 28 can be perfectly divisible by 7, right? So I can't get a fraction where the denominator is going to be other than 2 and 5, which is going to divide 24x and 28x to give me an integer, right? I will not be able to get 3, I will not be able to get 7. Not 5, not 5. I don't need the 5 here, right? Because I can't get any denominator to be 5 because it's not 24 into something, which is a fraction where the denominator is 5 will never give me an integer. How is 1 by 4 non-term? How is 1 by 4 non-terminating, Tarun? 1 by 4 is 0.25, right? 4 is 2 square, isn't it? No, Sanjana, I was just reiterating the fact what is the definition of a terminating fraction, right? So the terminating fraction is where you have the denominators to consist of only 2's and only 5's, right? So here you only have to get 2's and 4's. That's the only possibility. Okay with this, guys? Everybody? 1 by 4 is definitely terminating, Tarun. No, the answer is C, right? Because the combined statements are definitely sufficient to answer the question, right? When you combine the two statements, the answer is C. When even the combination of the statements is not sufficient, then we answer E, right? That's how you work with the data sufficiency. All right. So yes, 24x and 28x are both integers. That's what the statement gives us, Santosh. All right. Any other doubts, guys, on this question? Can we move on to the next one? What is the LCM got to do with this, Santosh? I need to find out whether X is a terminating decimal or not. I'm not worried about what 24X is and 28X, right? The question is asking me information about X, and X has to be between a value from 0 to 1, right? That's what the question tells me. All right. So, guys, another pretty easy one based on the concept of terminating. So here's question 4. Same rule applies. 2 minutes. We're going to have a discussion at the end of 2. Please do not type in the answer before I make a mention of it. All right. Your 2 minutes starts now. All right, guys, you can start typing your answer, please. Okay, I see most of you have given me B, some have given me D, some with C. Okay, I'm waiting for some more answers. I mean, I have 46 people still logged in, so I've only hardly got around 15 to 20 responses. So guys, okay, so a lot of B's, a lot of D's, some C's. So let's look at it. Okay, let's look at it. You need to be a little careful in reading the question. Okay, for those who given Delta as the answer and those who given Charlie as the answer, you need to be very careful in analyzing the questions first. So I've been told that A, B, C, D, and E are all integers, and M is 2 to the power of A and into 3 to the power of B, and N is 2 to the power of C into 3 to the power of D into 5 to the power of E. And the question is M by N a terminating decimal? Right? Now, for M by N to be a terminating decimal, think about it, okay? M by N to be a terminating decimal, this is 2 to the power of A into 3 to the power of B divided by 2 to the power of C into 3 to the power of D into 5 to the power of E. Now, the definition of a terminating decimal is that the denominator should consist of only 2's, only 5's, or only combinations of 2's and 5's. But if the denominator consists of anything other than 2's and 5's, right, then definitely it would be classified as non-terminating. So what I need importantly here, if I analyze this question, is for M by N to be terminating, I need some piece of information which cancels out the 3 in the denominator. And if I have some piece of information which cancels out the 3 in the denominator, I can definitely for sure say that M by N is definitely a terminating decimal. I don't need to worry about the 2's, I don't need to worry about the 5's, because for a terminating decimal, the denominator has to contain 2's and 5's, right? Now, if I look at the first statement tells me A is greater than C. Now, if A is greater than C, then I know that 2 to the power of A will definitely cancel out whatever is there in the denominator in terms of 2 to the power of C. But it still doesn't cancel out the 3 to the power of D, right? Because 3 to the power of D makes the answer non-terminating. Agree? Okay with this? So if I tell you that A is greater than C, I know that I still have 3 to the power of D in the denominator, which doesn't cancel out. So it is possible for me to get a non-terminating fraction if I'm left with 3 and 5 in the denominator. It's also possible for me to get a terminating fraction because I have no information about B and D if 3 to the power of B and 3 to the power of D cancel out, leaving me only with 5 to the power of E. So for the first statement is clearly insufficient, and the 3 possible answer choices are B, C, and E. Okay with this, guys? Okay with the first statement? How I analyzed it? See, the key to solving any data sufficiency questions, right, is not to jump into the statements directly. It's for you to first figure out what the question asks you to find out. So when you analyze the question, you'll realize that everything would hinge upon the values of B and D because it's the powers of 3, and I need to somehow eliminate the 3 in the denominator for me to say that M by N is terminating. Okay with the first statement? All right. Now let's look at the second statement. The second statement tells me that B is greater than D. So I have 2 to the power of A into 3 to the power of B divided by 2 to the power of C into 3 to the power of D and 5 to the power of E. Now if the value of B here is greater than the value of D, then I know that I can cancel out the denominator completely. For example, if B is equal to 3 and D is equal to 2, I'm going to get 2 to the power of A into 3 cube divided by 2 to the power of C into 3 square into 5 to the power of E. Now I have enough terms in the numerator to cancel out the 2 3's on the denominator, right? So when I cancel out the 3 in the denominator, all I'm left with in the denominators are 2's and 5's. So the second statement clearly is sufficient for me to say that M by N is terminating. So the answer here is B. Okay with this, everybody? So the second statement is definitely sufficient, right? Because it gives me a terminating fraction since I'm left only with 2's and 5's in the denominator. Doesn't matter at all, Arun, if you consider a negative, right? Because at the end of the day, you need to work with the statements, right? Consider a negative and see what happens. Consider a negative and see what happens. So if I take B to be minus 2, and I take d to be minus 4, then what happens? Think about it, right? Think about it. If I take b to be minus 2 and I take d to be minus 4, the terms of 3 would switch, right? The powers would switch, and I would still get the denominator to be lesser. I would still get the denominator to have lesser number of 3's than numerator. I'll show it to you here. Okay, say we take b is equal to minus 2, okay, and we take d is equal to minus 4. So this becomes 2 to the power of a into 3 to the power of minus 2 divided by 2 to the power of c into 3 to the power of minus 4 into 5 to the power of e. Now, if I simplify, right, to make the exponent positive, we can always flip the entire fraction, right? So 2 to the power of a, so this becomes 1 by 3 square, and the 3 to the power of minus 4 goes on to the numerator to become 3 to the power of 4. So this would be divided by 2 to the power of c into 5 to the power of e. That would still give me enough information to cancel out all the 3's in the denominator. Agree, Arun? This is specifically for you. Okay with this, Arun? Perfect. So it doesn't change the answer at all, right? Because even if we take a negative exponent, I need to take it to the numerator and make it positive. Okay, guys. So it was a really good doubt, okay? Because what I did here is I ended up using only positive integers, and I worked with it. But when you change it to negative, right, you need to understand that it still goes to the numerator, and the lower quantity still comes to the denominator. Perfect. All right. So I'm guessing you have some clarity on what terminating fractions are and non-terminating fractions are. What is the level of this question? It's a very bad question to ask me, Abhishek, because I would, I wouldn't classify questions based on levels. So I would say if you ask me on a personal level, how much would I classify this question in terms of a 200 to 800 scale? I would say 600. Okay, not even 600, 580 level question, because it's way simple. All right, perfect. So I'm going to move on to the next question, right? And I want all of you all to try solving this. And then once you solve this and give me an answer, I'm going to deal with the concepts involved with what is discussed. All right. So here's the next question. Another 30 seconds. You can start typing your answers in the chat window, please. I've got only 5 responses so far. Last 10 seconds, guys, so please make sure you type in your answers. All right, so a lot of different answers here, some C's, some B's, a lot of you all with E. What concept is being tested? I just want you to quickly type in the chat window, what concept is being tested with this question? Powers, yes. So not powers exactly. So no, it's not testing in exponents. Exactly. It's testing you on the concept of prime factorization. Okay, it's just the worded form of a prime factorization question, right? So what you need to understand here is whenever you see keywords like this, right? What the last part of the question tells me, the product of the point values. Now, whenever you see this statement, the product of the point values, you know that it's basically a multiplication of all these terms that are given to you. And remember, when you factorize any number, when you factorize or you prime factorize any number, the definition of prime factorization is you break down the number into a product of its primes. So I've been given 4 types of chips: blue, green, purple, and red. And they've also given me the point values of each of the chips, right? We have the blue, which has 1 point, the green, which is 5, X, and 11, right? Now, they've not told me exactly what the point values are going to be equal to. So they've just told me that the purple chips are going to be worth more than the green chips. The purple chips are going to be worth more than the green, so that P is going to be greater than G, but lesser than the red chips. So R is going to be greater than P, is going to be greater than G, right? And a certain number of chips are then selected from the bag if the product of the point values of the selected chips is 88,000. So what they've given me is the product of all the point values. So I'm going to take 88,000 and I'm going to break it down, into its prime factors. Okay, so I have 11, 5, and 1 given to me, and I also have a value of X. So I'm just going to first divide this by 11. So 11 8s are 88, 8,000. I'm going to divide by 5. 5 1s are 5. 5 6 are 30. Again by 5. 5 3s are 15. 5 2s are 10. 0. Again by 5. 5 6 are 30. 5 4s are 20. And then finally, I'm going to have 64, which can be broken down into 2 to the power of 8, right? 2 to the power of 6. Now, you can break down 88,000 as 11 into 5 cube into 2 to the power of 6. Now, what you need to understand here is you need to tell me what can be the possible value for X. What can be the possible value for X? Based on the fact that the red chips cost more than the purple chips, cost more than the green chips. So for those of you all who factorized to this form, how would you analyze it from this point? So quickly, please type in the chat window, how would you analyze the question and how would you give me the answer based on this factorized form of 88,000? Perfect. Perfect. So what you need to understand here, is I know that the answer has to be in between this 2 to the power of 8. I know that point values of the red chips are much greater than the point values of the purple chips and much greater than the point values of the green chips, right? So this can be written as 11 into 5 cube and 64 can be written as 8 square. So I know for a fact that the value of X here has to be 8. And the question is asking me how many purple chips were selected. I'm going to select 2 purple chips because I need to get a 64. So 8 square is going to be equal to 64. So the answer here has to be B, 2. Right? The key piece of information given this question is the fact that the red chips cost greater than the purple chips and cost greater than the green chips. Right? So if red costs greater than the green, red costs greater than the purple and greater than the green, the value of the purple chips has to be between 5 and 11. So the value of the purple chips has to be between 5 and 11. I need to break down 64 into a square of a number which is between 5 and 11. And the only possibility here would be 8 square, right? So I can break down 88,000 as 11 into 5 cube into 8 square, which gives me the number of purple chips to be 2. Okay with this, guys? Sanjana, I don't think you need to worry about what level the question is. This would be slightly of a mid 600 level, right? It's a very bad it's a very bad process for you to look at what levels the questions are. Okay, you just need to understand that the basic concept that is being tested here is prime factorization. Okay, with this, guys, it's a very simple one. It's a very simple one which asks you to break down a number. So why did I give you this question before I'm going to discuss discuss the concept is because of this. Okay, so I'm just going to exit from the PPT here. And I'm going to open a new Word file. I'm going to discuss a little bit about what prime factorization is and what are the applications of prime factorization, also in terms of factorials and also in terms of remainders. Okay, so what is prime factorization? Like I said, prime factorization is when you break down a number into a product of its primes. For example, if I take 225 and I break down 225, this would be 3 7s are 21, 3 5s are 15, 3 2s are 6, 3 5s are 15, 5 5s are 25, and 5 1s are 5. So 225 can be written as 3 square into 5 square. Now this way of representation is called the prime factorization representation of a number. Now if you represent any number in terms of its prime factorization, right, it's going to give you a lot of applications. Now, the two best applications that the GMAT normally would test you on in terms of prime factorization is, prime factorization tells you if a number is a perfect square or a perfect cube. How, by looking at a number, can I figure out if it's a perfect square or a perfect cube? If I prime factorize a number, right, for example, 3 square into 5 square, and I see that the powers of the primes here are all divisible by 2, then that number is always going to be a perfect square. And if I prime factorize a number and I see that the powers of the primes are all divisible by 3, then that number is always going to be a perfect cube. So for a number to be a perfect square, the powers all have to be divisible by 2. And for the number to be a perfect cube, the powers have to be divisible by 3. So it's logical to say that for a number to be a perfect square, the powers have to be divisible by 2. For a number to be a perfect cube, the power has to be divisible by 3. And for a number to be both a perfect square and a perfect cube, the powers have to be divisible by both 2 and 3. And both 2 and 3 will correlate to 6, right? So for a number to be both a perfect square and a perfect cube, the powers have to be divisible by 6. So the first application of prime factorization is it tells you if a number is a perfect square or a perfect cube, okay, just by looking at how the powers are going to be divisible by 2 or by 3. Now the second application of prime factorization, and this is the more important application here, is if you take the prime factorized form of a number, looking at the prime factorized form, you can comment upon how many factors a number has. Okay, you can speak about the total number of factors a number has. Now, what are factors? Factors are numbers which perfectly divide another number. For example, if I take 4, right? The factors of 4 are 1, 2, and 4. 1, 2, and 4 perfectly divide 4. So they're called factors. And factors and divisors are exactly the same. So now, if I need to find out the total number of factors of a number, I'm first going to write the prime factorized form of the number. And what do I do with the prime factorized form? We take the power, add 1 to it, take the second power, add 1 to it. So this would become 3 into 3. I'm going to get 9. Basically, the general form here is, if you have a number which is prime factorized in the form of p1 to the power of k1 into p2 to the power of k2 till pn to the power of kn, till pn to the power of kn, then the total number of factors of any number would be given by k1 plus 1 into k2 plus 1 till kn plus 1. Right? What you need to do is just take the powers, add 1 to them, and multiply them. The product of those powers, right, are going to give you the total number of factors of a number. So the most important application of prime factorization is it gives you information of how many factors a number is going to have, right? For example, if I give you say 3 square, if I give you 3 square into 5 cube, and I ask you how many factors does 3 square into 5 cube have, what will be your answer for that? Think about it. If I give you 3 square into 5 cube, and I ask you how many factors does 3 square into 5 cube have? Perfect. So this is going to be 2 plus 1 into 3 plus 1. So 2 plus 1 is 3, 3 plus 1 is 4. So 3 into 4 gives me the 12, right? But think about this now, okay? What if I give you this 4 square into 5 cube? And now I ask you for 4 square into 5 cube, what are the total number of factors? What would be your answer for this? $20? Perfect. The answer is not going to remain 12, okay? So that's a common error that people will make here. Remember when I spoke about p1 to the power of k1 and p2 to the power of k2, you have to make sure that the base is prime. So 4 square is going to be written as 2 to the power of 4 into 5 cube. And now you're going to apply the formula. So you're going to take the power, which is 4, add 1 to it. You're going to take this power, which is 3, add 1 to it. So 4 plus 1 is 5, 3 plus 1 is 4. So 5 into 4 gives you 20. So the total of 20 factors for the number 4 square into 5 cube. Okay, so the most important application is of prime factorization is it gives you information about the total number of factors, and you can figure this out all by looking at the powers, as long as you make sure that the bases are prime. All right. Okay, so since we're dealing with factors, right, I'm just going to move into the um, realms of factorials, as well as I want to make a point also in terms of powers. Okay, so I'll deal with factorials first. Now, if I give you a question, okay, and I'm going to draft a question here, and I want all of you all to take around a couple of minutes to solve this. What is the greatest prime factor? What is the greatest prime factor of 11 factorial into 12 factorial plus 12 factorial into 13 factorial? Okay, I'm not going to give you answer choices. I want you all to figure it out. So my question is, what is the greatest prime factor of 11 factorial into 12 factorial plus 12 factorial into 13 factorial? Okay, I'm going to give you 2 minutes. Think through it, think through the question, and give me the answer at the end of 2 minutes. All right. So some of you all have told me 13, some of you all 157, some 11, some 7, 157, and so on, right? Now, there's a couple of things that I want to, I want to point out here, okay? See, whenever you're dealing with factorials, right, and whenever you're dealing with powers, whenever you're dealing with factorials and powers, you always make sure, since they are derivatives of prime factorization, you always make sure that when you have an addition of values, you remove the addition by making it into a multiplication of values. You do some manipulation of the equation so that you end up with a multiplication of values, because it's going to be easier for you to work with multiplication rather than with addition. Now, for some of you all who gave me 13 and 11 as the answer, that's definitely not going to be the answer. You have not simplified the factorial to the lowest form. So as soon as you see something in terms of factorials, or as soon as you see something in terms of powers, right, where you have addition and subtraction, your first working procedure, the first step of the working procedure that you need to apply on this question should be to convert the additions and the subtractions to multiplications. Because when you convert into a multiplication, right, I can easily comment on what is a prime factor, because the only way I can comment upon prime factors is if it's a multiplication of values. So I'm going to pull 12 factorial out common here, okay? So that's going to be 11 factorial plus 13 factorial. And out of 11 factorial and 13 factorial, I have 11 factorial, which is common. That's 12 factorial into 11 factorial into 1 plus 13 into 12, right? Because if I pull 11 factorial out of this, what 13 factorial is 13 into 12 into 11 factorial, right? So I'm left with 13 into 12. So I have 12 factorial into 11 factorial into 157. Now here I've converted this entire question into a multiplication of values. So when you convert the entire question into multiplication of values, it becomes easier for you to figure out what is going to be the factors and what is going to be the greatest prime factor in this case. Now the only problem you're going to face here, is clearly you've broken down the number into 12 factorial into 11 factorial into 157. So can you break down 157 further into a product of two values, or is 157 definitely a prime number? How can you for sure say that 157 is a prime number? On what basis are you telling me that 157 is a prime? Okay, so one way of representing a prime would be in the form of 6k plus or minus 1. Guys, you need to be a little careful, okay, when you work with 6k plus or minus 1, because you need to understand there are certain restrictions to using that 6k plus or minus 1, okay? All prime numbers other than 2 and 3 can be represented in the form of 6k plus or minus 1. But the reverse doesn't hold good. All numbers which can be represented in the form of 6k plus or minus 1 are not primes, right? So if you're using the 6k plus or minus 1 here, in this question it's going to work fine, but on all questions it's not going to work fine, because I told you, right, it works one way, it doesn't work the reverse way. So the best way, right, the best way for you to figure out whether a number is prime or not is to take the closest perfect square slightly greater than the number. So the closest perfect square slightly greater than 157 is 169. That is 13 square. So what you're going to do, once you find out the closest perfect square slightly greater than the number, you're going to divide that number by all the primes up to the closest perfect square. So all the primes up to the closest perfect square, which is 13, are 2, 3, 5, 7, 11, and 13. So now for me to comment on whether 157 is prime or not, if 157 is not divisible by any of the numbers 2, 3, 5, 7, 11, and 13, I can for sure say it is prime. But if 157 is divisible by any one of these values, 2, 3, 5, 7, 11, and 13, it will not be prime. So 157 is definitely not divisible by 2, not divisible by 3, not divisible by 5, clearly not divisible by 11 and 7. 13 ones are 13, 13 twos are 26, so it's clearly not divisible by 13. So 157 for a fact is definitely a prime number, right? So the greatest prime factor of 11 factorial into 12 factorial plus 12 factorial and 13 factorial is 157 and not 11 and not 13. See, the point that you need to take back in this question, right, is whenever you have factorials and you have an addition or a subtraction, you always try to take terms common and make it into a multiplication of values, because once you make it into multiplication of values, it becomes easy for you to figure out what the prime factors are going to be. Oh, what the hell happened? So what did you understand, Vivo? So if you can tell me what exactly is your doubt, I can, cater to that specific doubt rather than me, going through everything all over again. I'll be conducting the webinar till 6 p.m. Sanjana. You don't need to worry. I'm not working with the unit digits, Tarun. What I'm saying is, for a number to be a prime, I need to find out the closest perfect square slightly greater than that number. And what you do, you try dividing by that number by all the primes up to the closest perfect square. So what I do, I try to divide 157 by 2, 3, 5, 7, 11, and 13. All the primes up to the closest perfect square, right? So I realize that 157 is not divisible by 2, 3, 5, 7, 11, or 13. So I can for sure say that that number is prime. Okay, that's a rule. That's a rule of figuring out how a number is prime or not. Okay, that's the easiest way. Okay, guys. So based on this concept, right? Based on this concept, I'm going to give you a challenger question. Okay, and I want you to think about this. It's a good. I would, for people asking me what is the level of this question, I would definitely classify this as a good 700 level question. Okay, so here's your challenger question based on the concept we just discussed, but in terms of powers. So I'm going to give you 2 minutes. We're going to have a discussion at the end of 2. Another 30 seconds, guys. Waiting for an answer. I've got only one answer till now. All right. So most of y'all have given me alpha, some of y'all beta, one or two with Charlie, a couple with delta. Okay, why is this question a hard question, right? Is because now you need to be very, very careful here. 4 to the power of A plus 4 to the power of B plus 4 to the power of C plus 4 to the power of Q is equal to 4 to the power of 32. And the question asks you for A plus B plus C plus Q. Now the big problem that you're going to face here is you have an addition of all these quantities. Now we know all the properties of indices, right? We know what is a to the power of m into a to the power of n, a to the power of m divided by a to the power of n. But I don't know what to do if I have a to the power of m plus a to the power of n, right? I just have to leave it as it is. So the tricky aspect of this question is how do you simplify this question to get to what the question asks you to find out? Now think about this. The big clue here, right? The big clue here is the number of times 4 to the power of A, 4 to the power of B, 4 to the power of C, and 4 to the power of Q are added is 4. Basically, you're dealing throughout this and dealing with this entire question where you have 4 terms, you have the base to be 4 everywhere, right? Now, what I'm going to do is I'm going to write this right-hand side of 4 to the power of 32 as 4 into 4 to the power of 31. I'm trying to make it a product of values. And why am I choosing 4 into 4 to the power of 31? Because I have 4 terms on the left-hand side. Now think about this logically, okay? Think about this logically. For the left-hand side to be equal to the right-hand side, the only way the left-hand side can be equal to the right-hand side is if A, B, C, and Q are all equal to 31, right? A, B, C, and Q are all equal to 31. The logic here is x plus x plus x plus x gives you 4x. So the only way the left-hand side can be equal to the right-hand side is if the powers, that is A, B, C, and Q, are all equal to 31, right? Because if I have 4 to the power of 31 plus 4 to the power of 31 plus 4 to the power of 31 plus 4 to the power of 31, this is going to be represented as 4 into 4 to the power of 31, right? So I know for a fact that A is equal to B is equal to C is equal to 2 is equal to Q is equal to 31. And I need the value of A plus B plus C plus Q. So A plus B plus C plus Q is going to be 31 plus 31 plus 31 plus 31, which is 124. Okay with this, guys? It's a very, very tricky one because you just can't equate the powers directly, right? just can't equate the powers directly and say a, b, c, and d. A plus b plus c plus q has to be equal to 4 to the power of 31. You're going against the rule of indices, right? So what I do, I had to make the left-hand side to be equal to the right-hand side. So I ended up keeping all the values a, b, c, and q to be equal to 31, and I kept it in the form of x plus x plus x plus x, which is equal to 4x. Okay with this, guys? All of y'all? Perfect. Okay, so that's my first part. This is the first, half of the number system topic. Next week, when I meet you again on Saturday or Sunday, whenever the day the webinar is scheduled, I'm going to deal with the second bit of the number system topic. I'm going to deal with concepts of remainders. I'm also going to deal a little more in depth about the concept of factorials. I'm also going to deal with, somebody mentioned the unit digit concept. I'll discuss the unit digit concept, and I'll also continue with the same set of slides that I have with the other challenger questions, and I'll also try to include another couple of 700 to 800 level questions. Okay, so we'll stop the first part of number systems here, right? I don't want to continue further because if I do so, it'll take me another half an hour, and we have the webinar only scheduled till 5:30. So I've already taken 20 minutes extra. So we're going to stop here. I'm going to meet you again next week, same time, right? And we can discuss the second part of the number systems topic. All right. All right, guys. Have a great weekend. Good evening.